Good afternoon. We are the Master Mechanicals, and we're here today to present our design presentation number 1 for our hovercraft design for our Term 8 project. So our group members consist of myself, Greg Williams,
Justin Tibbs,
Brandon Pilgrim, Josh Boyd.
So here's an overview of the presentation that we're going to give today. We're going to start off with the problem statement, design constraints, background research, general hovercraft design, then we'll get into our hull and skirt designs. We'll also talk about our controls being used to control the hovercraft, the accessories, the design calculations that we're going to be used, and the conclusion. So a problem statement is design and fabricate an operational hovercraft. The hovercraft will have surveillance capabilities. We have an estimated budget of $500 with $250 reimbursed by the engineering faculty. So design constraints that we are faced with for this project is the maximum lift that we can generate from our propeller. This then in turn determines the weight of our hovercraft, the cost of fabrication, the parts availability for our hovercraft, time constraints of fabrication, and the safety during use.
So some background research on the hovercraft. The hovercraft operates based on lift and propulsion. If there's too much airflow, you have a higher altitude and the stability is weakened. If there's not enough airflow, the hovercraft will not get any lift and therefore not move off the ground. As you can see from the picture on the right, air blows downward from the lift propeller, which fills up the skirt with air. Then that will lift the hovercraft off the ground. The back propulsion motor will determine the steering and forward and reverse of the hovercraft. Some background research, we looked into 3 or 4 different types of hovercrafts that are currently in use. Some were built over in Europe and others were built in the States. The first one is the military issued hovercraft. As you can see, that it has a cylindrical shaped front, and it's for military purposes. It's used to carry passengers only. The Indian Griffin hovercraft is the world's largest hovercraft. It is used to carry passengers as well as additional payload besides. The Iranian hovercraft is also military, but the difference between this one and the original was that the shape is more of a helicopter shape and not fully cylindrical like the rest. The Mercier Jones Future hovercraft is the newest style of hovercraft. It was built in Chicago. The Mercier Jones Future hovercraft takes a body style design different than the other 3. Both propulsion motors as well are also in different locations. So for our general hovercraft design, for our purposes, we will need to use the skirt, the lift and propulsion motors, a fin along with a rudder, and instead of a radar on our design, we will use a video surveillance camera system.
Alright, so right now we'll move on to our selection criteria. So when it came to the selection of our components, we based it on 5 different items. There's our weight, our ease of use, our costs, our product availability, and our time. And all components, when it comes to our design matrices, are going to be ranked out of 20 points. And for our hull selection, here we have 3 hull material options. We have aluminum, molded plastic, and styrofoam/foam board. And right here you see our hull selection design matrix. So when you look at the matrix, for the aluminum, we ended up with a total of 80 out of 100. For our molded plastic, we had 50 out of 100, and for our styrofoam, we had 95 out of 100. So, which means we're most likely going to go with styrofoam for our hull. And another section of the hovercraft that we had to choose for is our skirt. So we had 3 choices. We had a bag skirt, a finger skirt, and a combination of both. So the bag skirt is the simplest design, both design and manufacture, and it's the best suited for multi-terrain. Our finger skirt is a little more complex. Will take a lot more time to design and build a finger skirt. The finger skirt is best suited for light racing hovercrafts because it has low coefficient of drag. And design also requires the use of an air chamber to distribute the air into each finger of the skirt. And bag and finger skirt, this one is a more complex skirt. And design incorporates the best of both the bag and finger skirts, so it would end up with low drag and multi-terrain capability. And right here you see our design matrix for our skirt selection. So bag skirt, we give 100 out of 100. Our finger skirt was 70 out of 100, and the bag and finger skirt was 60. Basically, Biggest reason for a bag and finger skirt to be 60 is just that we don't really have enough time to build a bag and finger skirt. It's really complex.
So next up, we have our controls section. So for this section, we had 4 different options available. We looked at video control, Arduino, a control board, and the RC control. So based on the 5 categories mentioned by Brandon, we ranked each option based on their availability, weight, ease of use, cost, and the time that we had for this short project. And this came up with the RC control. It also was a good option for us as we've already got experience with RC controlling. Next we have our motors. So as Justin mentioned in our background research, there's a number of different ways to design the hovercraft based on 2 motors on the back, where the speed can be changed in each motor individually. Or you can have 2 motors with fins and rudders to control the aircraft for steering. Or you can go with the simplest design with 1 motor with a fin to control the hovercraft. So here is the design matrix, and based on the 5 categories, it came out that we would go with this simple design, and that is the 1 motor with a fin. So then we had to decide on a camera system. So we had 3 different options. We could go with a wireless live feed, or a recordable camera system, and then a combination of the both. So for the camera system, we ranked each option, and then we kind of decided that it would be important for our hovercraft to have both of these capabilities. Therefore, it creates a redundancy in our system. So if the hovercraft ever failed to record the data, we also had our live feed that would give us the opportunity to react on a situation immediately. The design calculations will then be determined so we can size our hovercraft. So first we have our weight. That's basically dependent on how much accessories and our camera system, and that will determine what is required to lift the vehicle off the ground. So then from there, the lift provided will be based on the size of the motor and propellers that we purchase, and the drag force acting on the hovercraft, such as external aerodynamic drag, momentum drag of the lift system, cushion drag, and skirt drag. This will also help us determine the propulsion motors on the back. And the last one is thrust. The power produced by the thrust fans will overcome the drag force.
So for our design calculations, we calculated our lift force. We had to calculate the cushion pressure, the cushion flow rate, and the lift power that is required from our lift motor. For our drag force, we had our aerodynamic drag, our momentum drag, and our skirt drag. For the thrust force, and then we had to manipulate the thrust force equation to get the density, speed, and the area. So in conclusion, for our next step is move on to the detailed design process of our project. We have to determine our lift and drag characteristics and determine an estimated weight and how much lift we can generate with our motor. We need to calculate the size and shape of each of the components that will meet the lifting capacity that we desire. And we have to enter into the manufacturing phase of the project and begin testing the design we have generated. Thank you.
We did our whole presentation, like all